So what if we take a crystalline structure and we start adding different elements to it, alloys? So in structural materials, this is really where we abide by the strength and the different types of properties that we have. So we can put impurity atoms, we intentionally add them to really start to change some of the characteristics. And so we can use alloying to improve mechanical strength, corrosion resistance, any different number of properties that you can think of. Typically, we develop alloys for that. Think of even wear resistance is another good one, which we could tie into mechanical strength. So the good example I have is sort of pure silver versus sterling silver. Now, you don't see a lot of jewelry or other types of components like that made from pure silver. Pure silver itself is highly conductive, but it doesn't have a lot of strength, very much like gold. If we look at gold, pure gold is very soft. Now, if we're going to sell jewelry, we're not going to sell it as pure silver, but we're going to sell it as something called sterling silver. And sterling silver has a lot of the properties and appearance of silver, but it has the strength and the ability to be worked into complex shapes. Because if we really look at jewelry of different types, you can have a lot of complexity, whether it's in an earring or a necklace. And so with the sterling silver, we add about 7.5% copper to that silver. They are soluble in each other, so we can add the copper without it coming out of solution. But what it does is this impurity atoms in the metal create this alloy. And so we can form a solid solution. Now, two terms to think about before we move on too much further. The solvent, it's the element that is in the greatest amount. So solvent, largest amount. Solute is the one in a minor concentration. And so when we start talking about a lot of metallic systems, what we're going to see in these systems is they're what we call dilute solutions. And so with that, that means the solute is in a fairly minor concentration. If we think about even in sterling silver, 7.5% copper is a lot less than the remaining 92.5% silver that's in the alloy. So solvent, greatest amount, solute, minor concentration. So what types of solid solutions can we get? So what we're doing is we're taking that pure crystal and we're going to substitute some other atom into that crystal structure. And so we can do it two ways. We can substitute an atom that is pretty close to that size, so that will basically go in and substitute. So a substitutional solid solution. It'll substitute for the atoms in the primary crystalline structure or crystalline lattice that we might look at. Now, we can also take smaller atoms that will fit into these interstitial spaces. Remember when we talked about self-interstitials, we had made the point where the space is not big enough to support what the size of the host atom would be. So in these interstitial impurities, we can take atoms that can fit in these. The small impurity atoms, they tend to be a little bit larger, but the introducing of that strain actually will strengthen the material. Now, what types of materials do we have? Substitutional alloys. I like to look at Monel. It's a nickel copper alloy. And so if you play a brass instrument, in a lot of cases, you have some type of Monel that is used to make that instrument. Steel is the most obvious example of what an interstitial solid solution would be. And so steel is nothing more than iron with a small amount of carbon. And so if we look at the size of iron, or where iron sits on the periodic table versus where carbon sits, what we tend to see is that the carbon atoms are rather small, especially in this hard sphere models that we're interested in, and they can easily fit into these interstitial spaces or into these interstices, and they provide that additional strain. And so carbon has a significant strengthening effect on iron. And so what we see is that just that small amount of carbon makes steel, which is, when we really look at it from the 19th, 20th century, and even in today, is really one of the most important materials that we use. And so let's take a look at the video. This gives us an idea of where substitutional and interstitial defects in. And I like this video for a number of reasons, because it also provides a little background into some of the ideas behind the process structure property relations that we're really going to start building on as we move forward in the course.
To understand the benefits of heat treating processes, first requires an awareness of metal and alloy structures. When a molten metal solidifies, the atoms arrange themselves into definite patterns called crystal structures. The two most common crystal structures in metals are body-centered cubic and face-centered cubic. These crystal structures grow uniformly in all directions within each developing crystal. As the metal cools, these crystals are confined by the adjacent developing crystals, forming grains. The line of intersection between grains is called a grain boundary. Because the grains form independently, their crystal structures develop tilted in various directions.
The idea behind planes and directions.
Structures are held in place by electromagnetic attraction of neighboring atoms. If a force or load is applied to a metal, these electromagnetic bonds stretch, allowing the atoms to move slightly. When the load is removed, the bonds pull the atoms back into position. If the applied force exceeds the metal's yield strength, those electromagnetic bonds will break, causing permanent stretching or deformation. To make metals stronger and more resistant to deformation, it's necessary to strengthen their crystal structures. This is done by adding alloying elements, which are other metals or non-metallic elements like carbon. The addition of an alloy introduces foreign atoms within the crystal structure of the base metal, disrupting the structural uniformity. This disruption results in increased strength.
So it sort of hit upon what we're going to get to as we move forward in the course, where the idea behind alloys for increased strength are these crystalline defects that we add. So we don't necessarily need a perfect crystal. And so let's start thinking about what goes into defining what an alloy is. And so if we really think about it, we call them solid solutions, or another way to think about it is alloys. We know there are two types. There's substitutional and interstitial. Now, looking and thinking about it in a hard crystal, a hard sphere type of model for the solid solutions, a British metallurgist named Hugh Morotherick gave some real thought to this. He came up with a set of very simple rules. I would recommend that you keep in mind these rules because you will see them again soon on the first exam. But he really started thinking in terms of these hard sphere models and how do you make something a solid solution where you'll make an actual alloy rather than having maybe two elements that don't really combine well together and they will just separate. They become what we consider in the materials world to be immiscible. And so in substitutional solid solutions, he came up with 4 basic rules. And if you really think about it, they all are pretty obvious when you think about the hard sphere model. Atomic size factor. You want the atomic radii of the solute and solvent atoms to be pretty similar. In this case, we give a number about no more than 15% difference. That gives us a little bit of strain or residual stress within the lattice. Similar crystal structures. Electronegativities want to be similar. Because if we go back to your chemistry class, and if you remember where you formed compounds, you tended to have large differences in electronegativity, made them really want to form compounds. We don't want to form compounds. Compounds in metallic systems tend to be brittle, they tend to decrease in mechanical properties, and they're called intermetallics. And so we want to get away from those. So we want to have electronegativities that are similar. So the atoms don't come together and form a compound, but they can reside beside each other. And then we want to have sort of very similar valencies. And when we see these similar valencies, we tend to really see how we can just directly substitute one atom for another within the substitutional crystal structure. And so those valencies, and with metals, they're bound by metallic bonding. We want to maintain that metallic bonding. So you really think of these for substitutional solid solutions, they all make sense. Size, crystal structure, electronegativity, and valence. And you want everything to sort of be the same. You're making a replacement of one with another. And so you don't want the crystal lattice or the crystal structure to really see that much of a difference. That's what makes a substitutional solid solution. Now, for interstitial solid solutions, there are 2 rules. So they're different because in the case of the interstitial solid solution, we want the solute atoms to fit into the interstitial spaces. And so they have to be smaller than those pores. And we want them, once again, to have similar electronegativity, back to what we saw with substitutional solid solutions. with that, they won't form a compound. So we really want to avoid forming compounds for most of these. And so Hugh Murathuri came up with these rules. Now, these rules tell us a lot about where to expect. And really in alloy development, they are a couple of the first things that people tend to really take into consideration, even though they may not specifically call them out. Very nice, simple rules of thumb, things that you would really like to, if you're in the scientific realm, have something developed that's so elegant and, at least in the perspective that we're taking, so obvious to look at. So back to the idea behind how do we quantify how much of these that we have? So how do we make alloys? And really from a material supplier perspective, or we're a steel mill or an aluminum mill or nickel manufacturing facility, people who make metals look at it in terms of how do I make an alloy? And the way they tend to look at it is they look at mass balances for the most part. So if you want to make an alloy that has a nickel-based alloy, or make a Monel that has 30% copper, you will, for the most part, know the size of what you might consider your tundish, your ladle, your furnace. You know how much material that can take. And so you want to divide up the amount of nickel and copper so that you can make a 70-30 alloy. Now, weight percent is the easiest way to do that, and you'll see weight percent almost across the board. Weight percent is a way to look at how much a particular element relative to the total alloy weight. So when we talk about composition, we talk in terms of weight percent. So we have these mass of these two elements. We're literally weighing out these masses and what they are as part of that. It's a very, very simple way to look at it. It doesn't take into account too much else other than just the weight balance behind it. Now, atomic percent is another way to look at it. So rather than the overall mass of each element that we're adding into that ton dish or ladle or furnace, this is based on the number of moles of an element in relation to the total number of moles. And so when we bring moles into it, we need to bring in atomic weight. So we have a certain mass divided by the atomic weight. So when we look at atom percent, what we're going to see is a very practical way to look at composition is weight percent. A little more of the scientific way is to look at atom percent. So you're going to run into atomic percents when you're talking in terms of maybe some electronic material applications, some very specific alloy systems with very specific properties. Nitinol, which is a nickel titanium alloy. And you've all, for the most part, been exposed to it. This is what they make dental braces from. Is typically defined in atomic percent, and that is primarily because they want to maintain very specific compositions. And so we have two ways of quantifying alloying element additions, or solid solutions. So we see that the mass is, and we can convert between the two by knowing the composition and the atomic weight. So we can go from weight percent to atomic percent, or atomic percent to weight percent. So it's easy to convert them. So let's take an example. A 97 weight percent aluminum, 3 weight percent copper alloy. You may look at it and say, yeah, it's aluminum copper. Well, the thing to really, before we go too much further in this, is this type of alloy is the basis for the vast majority of what we call 5000 series, or 2000 series, I should say. 2000 series aluminum alloys are based on the aluminum copper system. So in this case, we know the composition is 97% aluminum, 3 weight percent copper. And we know from any periodic table what the atomic weight of the two are, the grams per mole. So how do we convert this weight percent to atomic percent? So we can take our equation and we start plugging and chugging. So we see what the weight percent of the aluminum is, multiply that by the atomic percent of the copper, and run through ours. And so what we see in this case is the aluminum actually has a little higher atomic percent than its weight percent. Think about that. It's because primarily of this lower atomic weight. So by weight, there was more of it there if we think in terms of moles. And in a lot of cases, we know that it has to equal 100. So it is a check on that. I like to solve for both to make sure that I didn't make a mistake in the first equation. You can take a shortcut, solve for one, and then just subtract the other one from 100. I don't always recommend that. just for the most part, because it's a check to make sure that you are getting and certain that you aren't making a mistake in one of your calculations. But the two numbers, since it's only a binary or a two component system, should add up to 100. So we've seen here is what we can do in terms of point defects. We know there's a certain number of vacancies, so you can expect on the exam or in your homeworks to see how to define the equilibrium number of vacancies and then how to define solid solutions. Let's move into linear defects. Now, in the dislocation, what we have is a linear or one-dimensional defect around which some atoms are misaligned. So it's what we look at as the definition of a dislocation. An edge dislocation is the most common one. The Berger's vector is basically the distance between, it's the interatomic spacing that we might look at. Now, an edge dislocation, we look at that symbol. It's equivalent of a perpendicular symbol. So it's telling us that something is perpendicular here. That's the one way to really look at why we use that symbol for that edge dislocation. And we use that because the edge dislocation itself is perpendicular to the orientation of the Berger's vector. And so that is one to remember. If I were you, I would highlight perpendicular here for an edge dislocation. The Berger's vector and the dislocation line are perpendicular to one another. And we can see how this edge dislocation is really defined by this extra half plane of atoms. And if we look at our image here, we see how it produces a distortion in the crystal structure, what we might consider the crystalline lattice. And so we define it as this half plane of atoms. So we have this distortion. The bonds are stretched a little bit here and they come back around. And if we imagine that moving through the crystal structure, we're going to see how that stress moves throughout the crystal structure. Screw dislocations are formed by a shear stress. So there's two different types of linear defects. We have an edge dislocation, which is perpendicular to the Berger's vector, and a screw dislocation, which is parallel to the Berger's vector. And I would highlight that as parallel. And so the way to think of a screw dislocation is it's formed by a shear stress. So we know from our other classes that shear stress is basically, if we would have a block, we would hold the bottom of that block firm, or we would restrain that, and we would be pushing along the top. And so what it does, it creates a type of shear stress across it. And that's the way to think of a screw dislocation. We're basically taking and slightly twisting. If you think about a screw, you're going to twist it either to tighten it or loosen the screw. So the screw dislocation does much the same thing with the crystal structure. And we can see how we get this extra sort of half plane of atoms here. But what is important here is that the dislocation line and the Berger's vector are parallel to each other. Now, these dislocations can change because if we really think about it, even from the simple schematic that we showed before with the tray full of metal balls, we saw how dislocations move through there. And we saw that we weren't dealing, even in that small number of atoms, with only a single dislocation. We know within a material that dislocations are present throughout. And the more that we strain or work hard in the material, the more dislocations that we form. So as we either put it in tension or stress or some type of shear, we're going to create more dislocations. And those dislocations are going to start interacting with each other. And so literally, you can get combinations of an edge dislocation and a screw dislocation. And then in real materials, these are dislocations. These were taken in what's called a transmission electron microscope. And now with this is really one of my favorite videos of looking at dislocation motion. And so as we look at it, we see how, in this case, what it is a small sample in a transmission electron microscope that is being slowly deformed. And what we see are the dislocations. We see them coming up and forming as it starts, and we can start to see them move. And in this case, we can see how dislocations will interact with each other. In some cases, they will run into other dislocations and slow down. We see how it's a start and stop with the dislocations. And we see these other areas here where small precipitates, where dislocations will run into those and actually wrap around them or be stopped by them. So seeing how these dislocations move, we start to see and get an understanding of how different defects can interact with each other within a material And even on top of that is, how do we stop them? That is how we strengthen materials. So when we get into our strengthening mechanisms lecture in a couple weeks, we're going to really need to think about how these dislocations move. And so crystalline defects in and of themselves, as I mentioned earlier, really define what the properties of that material are going to be.